It's my pleasure to introduce our first distinguished lecturer of the season, Catherine McGeoch, who's visiting us today from just down the road at D-Wave Systems Incorporated. Catherine was one of the founders of the field of experimental algorithmics when she wrote her PhD thesis on the topic back in 1986 at Carnegie Mellon University. She moved on from there to a faculty position at Amherst College and continued to be a leader in this emerging field. For example, she was the organizer with David Johnson of the first DIMAX implementation challenge back in 1990. This was a concerted cooperative effort among researchers in the US to advance the state of empirical or experimental algorithmics through study of combinatorial algorithms. And it was run out of DIMAX, which is the Center for Discrete Math and Theoretical Computer Science at Rutgers University. They organized a second DIMAX implementation challenge a few years later. I remember participating in one of those many years ago. She also helped to found the ACM Journal on Experimental Algorithmics, which was founded in 1995, and she became the second editor-in-chief of that journal. And she's written a book, a guide to experimental algorithmics, which is a great resource if you're interested in understanding the performance of algorithms both from a theoretical and an experimental perspective. In the last few years, Catherine has changed her focus to quantum annealing, quantum processors. She was lured to think a little bit about the benchmarking effort for the D-Wave Systems quantum annealing processors a few years ago and has really enjoyed her work there and is now full-time at D-Wave Systems. So today we'll hear a little bit more about her work there and about the state-of-the-art in quantum annealing computing. Please join me in giving a warm welcome to Catherine.
Thank you very much for that nice long introduction. So, it's kind of been an interesting ride in the last few years. My background is in algorithms and heuristics for NP-hard problems and how to design experiments that actually tell you something rather than being inconclusive, which is easy to do in that field. And just really very recently, I was contacted by recently in professor years, about 3 or 4 years ago, by this fellow Geordie Rose, way out in the other side of the continent, who told me he had this quantum system that they're building, and they needed some help with how to evaluate it, and could I help him out? So I kind of did a job of work, a consulting job for them during a sabbatical, but one thing and another, and I'm just really in the last couple months have switched careers. This is my second career now. So there's a lot of, are there any physicists in the audience? I'm wondering. So yeah, there's been a lot of ramping up in physics for me, but I have maybe a tourist understanding of physics now, and so I can say the pen of my aunt is ferromagnetic, and that'll work. So how many have heard of D-Wave? It's a local company, right? So, and as you probably know, there's been like this huge swing of is it real, is it not real, is it good, is it bad? And the press kind of gets a little hysterical, I think, whenever you use the word quantum. But the company's been plugging along since like 2011, I guess. It's made its first. It's been around for 15 years, but they only started making quantum computers since about 2011, and so they're plugging away, manufacturing and selling these quantum annealing devices, which I'll talk about in a minute. Currently, they've got 3 systems that have been sold and are off-site, and a few systems online in Burnaby at any time. So there's like 5 of these machines running in the world right now. It's very early days. Think back in the 60s when we were looking at ENIACs. That's kind of where we are with these things. So there's a lot of different opinions in the press. I think my favorite quote is like, nobody knows how it actually works. And there's a really fundamental sense in which, yeah, the company did not wait for the theoreticians to tell them that this is going to work. They just said, let's build it and see if it works. And so there's this highly empirical approach to the technology here. And a lot of unknowns. I mean, completely new model of computation and things. And so I'll talk about that interface between theory and practice, what the theory says it should do and how it actually works and what it actually does. And so, yeah, so for you physicists out there and you computer scientists, be aware there are it's like physicists have different words for everything. And so do please interrupt me if you don't know what a word means, because it'll be a much more pleasant experience rather than not knowing. And I'm happy to try to explain. I'm almost dual lingual in certain things, but if I don't know the answer, I'll go physics, and we'll just go on, and I'll see what I can do. So, all right, so let me start by just kind of going over, and this is also a pretty high-level talk, because I, like most computer scientists that I know nothing about quantum computing and how those qubits work and things like that. So we're really starting with, I assume you have computer science, and you've heard the word qubit once before, and that's probably where you need to be in terms of background knowledge. So I'll talk about what the premise is, why people seem to get all excited about quantum computing, and how that relates to solving NP-hard optimization problems, model of computation, and then the interface between, I'll talk about quantum annealing. And you'll see, by the way, I have found several quotes from the big philosophers of our time, so I hope you'll enjoy this running commentary on the interface. So why quantum computing? There's this plausibility argument that says, look, if you have a classical computer with a 3-bit register, 110 is my 3-bit register there, and it's exploring a space of all possible combinations, all possible states, then it has to move from state to state, changing one qubit at a time. There's 3 to the n states here, or there's 2 to the n states for n equals 3 in this case. And you can only represent one state at a time if you have a classical computer. If you have qubits, then that might be my phone beeping, so just ignore it. Then what a qubit can do, it's a quantum bit, is instead of having either the state 0 or 1, you can think of it as being able to represent all the both of those states at the same time according to a certain probability distribution. And the probability is represented by that vector in this sphere and complex space. And so instead of 3 bits, you can have 3 qubits, each of them representing a probability of being, the poles in this case would be 1 or 0. The north and south pole would be 1 or 0, but while it's computing, you can represent all possible states, and because of coherent operation, another property that qubits have, you can change all of them at the same time in one step. So there's this sort of potential for being able to go through a set of states exponentially faster than a regular classical computer could do. That's the hand-wavy, oh, this has got to be great kind of argument. So the question is, yeah, but what problems would actually require you to go through all possible states? And can you actually build one? Can you get it to work? There's a lot of what ifs that follow up on that question. Okay, so that's quantum computing. Any questions? That's how it works. Okay, great. So zip all the way over to the other side of our mental map to computer science. And in particular, when you're wondering what problems, the approach that D-Wave has taken is not to build a universal computer that solves all problems, but to focus on a restricted device that solves NP-hard optimization problems. These are like NP-hard decision problems. There's a sort of a parallel class there, except instead of trying to verify yes or no the answer to the question, you're trying to minimize an objective function. You're trying to find the minimum cost solution that maybe has certain properties. So there are these sort of analog classes. There's NP-complete problems, and you can solve NP-hard optimization problems that would give you a way to solve the NP-complete problems. And there's this interesting relationship. So if, kind of a couple differences is everybody knows, right? Who knows this? You can verify, if it's an NP, you can verify the solution in polynomial time. I know this, yeah, see? But in optimization problems, you can't verify that you have an optimal solution. You can verify that it's feasible, a valid solution, but you don't know that it's optimal or not. So that's one kind of interesting difference. And also optimization NP has some subclasses according to how close it's possible to get an approximation. All right. One particular NP-hard optimization problem that we're interested in is called Ising model. It's in a different formulation. It's quadratic unconstrained Boolean optimization, and it's also maximum weighted 2-sat. Basically, the Ising model is defined on, the variables are +1 and -1. They're called spins. QBO is defined on Boolean values, 0 and 1, and weighted max 2-sat is defined on Boolean, like true, false values. So I should have said binary, but they're all the same problem, just depending on how you formulate them. But basically, the idea is that you're given weights h, which are applied to the vertices of some graph, and you're given some weights j that are applied to the edges of the graph. And your job is to find spin values, +1 and -1. We think of them as up and down. I do this a lot, to minimize this function on the spins and the weights. So basically, if h is a positive value, because you're trying to minimize that term, it's trying to make the spin be negative. A positive times a negative is negative, and you're trying for negative terms. If j is positive, it wants its two spins to be different. And if j is negative, it wants them to be the same. So these h's and j's are trying to, are working for and against your spins. So for example, if you have a particular spin configuration, -1, -1, +1, then you can see -1 times 2 is -2, -2 times -1 times -2. You can see how that particular solution gives you an energy, -1 in this case. All right? So if G is a non-planar graph, this is an NP-hard problem. There are these trivial transformations, and for those of you who know what it means, it has a p-TAS for graphs and for the particular graph structure that is used by D-Wave, for what it's worth. If you don't know, yeah, I will answer your question, but okay.
So sorry, you just said, so for what D-Wave does, the versions that D-Wave can solve, there is a p-TAS.
There is a p-TAS. There's not an f-p-TAS, but so it can. There's with this exponential prefactor, it can be solved in polynomial time, but it can't be solved in it's not known that it can be solved in polynomial time. All right. So basically, what we're going to try to do is use a quantum computing device to solve instances of the Ising model. And the way we're going to think about performance is these different configurations. Basically, it's going to end up with an answer that spins up and spins down, which can map to zeros and ones. And these represent the corners, the solution space of some hypercube solution space, right? And each corner has a value according to what the energy function does. And this gives you, it's really a discrete space, but I couldn't draw a discrete function that basically for each configuration of spins, minus, plus, 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 minus, you get some energy value. And what you're trying to do is find the global minimum, okay? That would be the lowest space in what we call the solution landscape. It kind of is a conceptual device, and it really doesn't matter what the x-axis is. We're just trying to point out that there are hills and valleys. Usually things that are close in Hamming distance tend to be near each other in the space, but But it's just, I'm trying to introduce you to this conceptual device called a problem landscape. It has hills and valleys. There's a lowest point, which is your ground state. And there are also points that are local minima, where, like the -3 there, every immediate neighbor has a higher value. And so if you change one bit for that local minima, you're going to get a higher value, and that's what a local minimum is. All right? So this is kind of a way we think about how hard these problems are. If the solution landscape doesn't have any hills, if it's a great big cherry bowl, then solvers, algorithms can just roll down to the bottom of the hill and use gradient descent methods to find it. But generally, these landscapes are quite choppy, and it's hard to know where you are and which way to go to find the ground state. Also called the optimal solution. That's physics and computer science mixing up. Okay, so adiabatic quantum computation. It's a type of computation that was introduced by Ed Fari at MIT in 2008. It's an alternative to gate model quantum computation. It's just a whole different computational model. And basically what you do in this, to solve a problem in this model, is you come up with these Hamiltonians. A Hamiltonian is just a matrix that describes the forces that you're going to apply to your qubits. Your qubits are going to be acting like a quantum particle process. They're quantum particles. They have spins up and down, states, superposition. They're doing all this quantum stuff. And you're going to apply forces to these qubits, starting basically from an initial state where everything's the same energy, same cost, and ground states are easy to find. And you make this slow transition, slow by slow I mean nanoseconds, it takes, in theory, from your initial state down to a solution landscape, a state landscape that matches the problem you're trying to solve. And as you go from initial down to final, the landscape starts changing. And there's a theorem that says if you change that landscape slowly enough, then if it starts in ground state, it's guaranteed to finish in ground state, guaranteed with high probability. And so this has got to work, right? This will be great. So basically, to specify an algorithm in this world, you say what you want your initial Hamiltonian to be. Usually everybody uses the same one. It's like everything's flat, but it doesn't have to be. You specify your problem Hamiltonian, which is the final state, where you want the qubits to end up. And then you specify this anneal path, which is basically a function A that takes your initial state from high to not there anymore, and a B that goes from nothing to full power. And you specify this transition from one state to the other. That's your algorithm. So you say, that's hard, there's no for loops. Okay? You basically say qubits, go like this, and then go to there, and then you read your answer. And so, yeah, that's the hardest thing, is to, yes?
It's not obviously good. How difficult is it to find this anneal path? Like, it seems like we're hiding some complexity in finding this anneal path.
Yeah, finding the anneal path. There must exist, there's hardly anything known, basically. It's known that, so basically what you've got to come up with a path that, I think I'll have a slide about this in a minute. How to find the right algorithm for the problem is just like in classical optimization. You try some things, except we have a lot less understanding of what's going to work and what's not going to work here. But yeah, some paths will give you a polynomial time algorithm, which means you have to, if it's a bad path, you have to run it for longer. This has to be done more slowly. And if it's a good path, you can do it quicker and maintain your guarantees, maintain your probabilistic guarantee of getting there. And how to find good paths versus bad paths, I'm telling you, this is not very old science. And in most cases, we don't know. We just try something and see if it works. Yes?
Is the anneal time related to the complexity of the problem?
Yes. in the following way. It's like I paid you, okay? So the anneal time is the time you have to go from T0 to some anneal time TA, right? That's how much time you're going to give it. And the adiabatic theorem of 1928, by the way, says that if you have a particle process, these are your energies over here, and there's a ground state energy, which is at the bottom, it's on the left, in your initial state. And you apply some forces, and you carry your particles, all the ground state will always be the ground state, and everything else is relative to it. But all the different energies of all the different states will change, and then you're going to get to the end. And if your time interval is slow enough with respect to what's called the spectral gap, it's the minimum distance at any time between the ground state and the first excited state, the next best state at any time. These can all change and everything. If you take a transition time that is proportional to a polynomial and 1 over the gap squared, then your probability will be high. But if your transition is too fast, then you have a higher probability of actually jumping the tracks and getting on one of those other states and getting arbitrarily bad. So it's got to be slow enough that based upon the spectral gap, you avoid this transition to the higher energy states. And the theorem from 1928, it's got to be real, says you're good to go. So that's fabulous, except for given input, there's no known way to really efficiently compute what the gap might be. And so again, this basically tells you that if in the problem size, if you can show that the gap grows polynomially in n, inverse polynomially in n, then you have a polynomial time algorithm. But in general, for inputs of any size, nobody knows how to compute what the gap is. So, hey, I ain't got no theorems, but we've got a machine, so that's cool. So we can try stuff, hey. So that's the theory, says that this is how this relationship works. And it was proved back, at the beginning of this millennium that this model of computation, adiabatic quantum computing, is polynomially equivalent to gate model quantum computing. So, it's universal, it's Turing equivalent, and it can do anything a gate model can do. So it's analog, it doesn't have gates and things like that, but you can express any Turing problem, any problem you can express on a Turing machine, and this will work, okay? So, in particular, they have these similarities. I don't know if anybody's ever seen, if you're going to design an algorithm in the gate model, it looks like a circuit, basically, because you're building these gates, and you're making a circuit out of quantum gates that have quantum properties that classical gates don't have. When there's no gates, there's these Hamiltonians, and there's this swishing motion that and so in particular, here's the two functions A of S and B of S that D-Wave uses. They kind of found it by trial and error, and there are some theoretical arguments that this ought to be a pretty good path. But theorems? You want theorems? No. I mean, there are some people who understand this more than I do have some arguments, about why this should be good. But again, there's nothing. It's highly empirical work. So you get these discrete gates versus a continuous analog computation. AQC is easier to actually build machines for reasons that I'll go into, but it's harder to make it universal. And in fact, the machine, the device that D-Wave makes is known to basically be missing it needs another term in the Hamiltonian. This is just the Ising model, but it needs a third term in order to be universal. It doesn't have it. They can put it in, and then it would be universal, but it's quite expensive. And they're kind of waiting for a reason to need to do it, I would say, before they do it. And gate model, the problem with gate model is it's hard to build, get these qubits to act together. It's hard to control them in such a way where instead of their state just falls apart, and then you have an answer you can't use. You're just getting random outputs. So The thing about AQC is you're trying to keep it in the ground state, and when qubits decohere, they want to decohere to the ground state. And since you want to keep them in the ground state, decoherence is not really the issue you have to struggle with. There are other problems, but they've got, but decoherence isn't really the objection. Yes.
Now, does this mean that if we really manage to scale up quantum computing, that there would be a transition at some point from annealing algorithms to gate algorithms? Because once you get the ability that you can build something with quantum error correction, then you're good to go, right?
Yeah, I think it is the case that there's the insights gained from building quantum annealers can be applied to building better gate model devices, but physics.
Okay.
Yeah, as far as I know, there's a lot of technology transfer that can be applied. How to control these things, is really the key issue. I think you'd still need your error, your thousands of error correcting qubits to get a gate model to work, but maybe you'd only need 1,000 instead of 10,000. I don't know. You're not taping this, right? Because I'm just spouting off uninformed guesses. So cut that part, please. All right. So what is quantum annealing? So we can distinguish, a lot of people use the two terms interchangeably. A lot of authors do and things, and that's fine. But it kind of where we are, me and my colleagues, is we're going to distinguish adiabatic quantum computing from quantum annealing. They're kind of the same thing, but I think of adiabatic quantum computing as like the Turing machine. It's the ideal computation. Adiabatic means basically that it's performed, the calculation is performed in perfect isolation from outside ambient energy, whereas real computers, quantum computers need that or else they get decoherence. So, on a real computer, you can't ever get perfect isolation from the outside world. So this is more like real world adiabatic quantum computing, sort of. And basically, quantum annealing was originally proposed as a classical algorithm, a classical heuristic that solves optimization problems. It finds ground states of optimal solutions to optimization problems. It's similar to simulated annealing, if you've heard of simulated annealing. But simulated annealing simulates a thermal annealing process. Molecules get hotter and colder and they go up and they go down, whereas quantum annealing simulates this quantum annealing process. Okay, it's a classical simulation of a quantum process. And it hasn't, it's quite well studied in physics, quantum annealing. It hasn't really, Holger can maybe tell me if he's ever heard of it in a it's slow to simulate, and it's usually, I think, not considered very competitive, but it's basically, similarly based upon these physical model of how quantum particles work. And the difference in the simulation is that, again, you have this flat landscape, you have a lot of random states. Classical computers can only have individual states, but they all move around probabilistically, and you can simulate this tunneling by making things move around in an X direction at random, and so it's meant to simulate the tunneling behavior. Whereas simulated annealing, you typically think of it as starting at one state, and it only has the solution landscape, and it goes up and down in that landscape according to temperature that it's trying to simulate. All right, so there are some cases where there are theorems that says quantum annealing is better than simulated annealing in terms of how fast it converges, but there are also, I believe, theorems in the other direction as well. So, yes?
I'm actually confused about those theorems because I don't understand what faster means in this context.
Let me think about that. Faster means, I'm pretty sure, a number of anneal stages to converge. So it's entirely asymptotic and not related to actual run times. Because the time per step in quantum simulated quantum annealing is quite large, because you kind of have to take a horizontal slice of your whole space and think about where could it tunnel to. But you have so many epochs of iteration, and so I believe right offhand that they are talking about convergence rates.
So the
Nothing
amount
else.
of effort per step is different for the two algorithms?
Yes. Yeah. So this was actually proposed well before Ed Fari came up with adiabatic quantum computation. But basically, as it turns out, quantum annealing algorithms can run on classical machines, like in simulation, or they can run on actual quantum machines being implemented on quantum devices. And so that's kind of a handy transition from one place to the other. And the D-Wave device implements a quantum annealing algorithm on a quantum device, using qubits, basically. All righty, we're good? Okay. So, backwards. Quantum devices can go backwards. So that was theory. Computer science, the theory, sort of the algorithmic premise, and why this whole approach is considered a viable approach, basically. D-Wave has built this machine, see, and it basically is meant to implement a specific quantum annealing algorithm in hardware. You give it it's wired in what the initial Hamiltonian is. You can change your final Hamiltonian according to the problem you want to solve. The anneal paths are hardwired in, but that might change in the future, that you could you can make some adjustments to the path. It's not adiabatic, which means perfect isolation. Perfect isolation is not possible in real life. So there's always some interference from the outside world that will kind of mess up the computation, and your probability of getting a ground state is reduced because of interference from the outside world. And on the current platforms, it's stochastic, and this is this thing I was saying about it's missing a third term in the Hamiltonian. That makes it stochastic, and they do know how to put it back in and could make it universal and polynomial equivalent, but at the moment it's not known.
What kind of interference could actually make it not adiabatic? Like what kind of?
Oh, any energy, any type of energy that physicists know about. Magnetic energy. They actually can detect earthquakes in California from seismic activity. They've got a little meter there, and you basically can't use it while there's an earthquake going on. Electrical, all of the gamma rays and all of those kind of things. Thermal energy, it has to be cooled, I'll show you in a minute, to 20 millikelvin, which is colder than deep space, really, really cold. But that's not perfectly cold, it's not 0 Kelvin. So basically the chip runs, and it's like Schrodinger's cat, you've got to really put it in the box and shut the door and wrap it up with lots of blankets in order to protect the computation. And that analog part is what happens when the thing is running in as highly shielded an environment as D-Wave can currently make. So any kind of energy can mess it up. And basically what they do is they implement that graph of nodes and edges physically with physical devices, and each node is a little ring of niobium, and it's got a magnetic field, and it can spin this way, or the electrical field can spin go this way or that way. It gives you a spin up, a magnetic field, except being quantum, it can be anywhere, and superposition all places at once. That's the part where we go like, okay. And also the couplings between them, the edges between them are also little rings of niobium that have the same properties and can make, you're controlling these rings, these loops that are all interconnected using these forces that are defined by the H's and J's. You set it all up, you shut the box, you watch it go, and then you read the answer at the end. The superposition states, once you read it, they all have to snap to +1 or -1, and you've got yourself an answer. It is probabilistic, it doesn't always work, and so the typical situation is you do this 100 times or you do this 1,000 times, and you see what kind of a distribution of answers you get. All right? I know, it's like, seriously? This is, really? But I tell you, this is really, how it works. So here's a picture of a D-Wave machine. It's about 8 foot high. That cabinet in the back is the highly shielded cabinet. And it's got these 3 processor racks in front. One of them is the, 2 of them are processors that are, there's a front end that receives problems from the internet and, schedules problems. And then there's all this control processors. This is a conventional Intel Xeon machines. And then the 3rd cabinet is the refrigerator, which is making it very, very cold. But so inside this chamber, which is like a commercial refrigerator, it's about 8 foot by 8 foot by 8 foot maybe, and meters. You guys are Canadian.
4 meters?
2.4 meters. Thank you. It's higher than me. And inside is this chamber, and there's this armature. It gets colder and colder and colder as you get closer to the bottom. And the processor is in this little chip that's mounted on the right with all these wires and things connecting it up. Really, really cold. Like super cold. And you can see that, you can't see all the shielding, but there's a lot of shielding going on. So what's on the chip? Basically, this chip has all these little qubits in this sort of grid-like arrangement that I'll go into more detail. They're all CCJJRF squids, for the physics majors and quantum engineers in the room. And it's made of, they're little loops made of niobium, basically. And then over on the right side, you can see there's control lines, and there's registers, and there's all that other kind of stuff you would expect to see on a chip to control it. And if you look at this little grid, it looks like this. Here's an 8 by 8. Is it 8 by 8? 1, 2, 3, 4, 6. 8 by 8 chimera grid. So 8 by 8 was the D-Wave 1. They're now 12 by 12, which is 1,000. Well, I'll tell you how that works in a minute. But on each of these little squares in this grid are 8 qubits. And the 8 qubits are these little red loops here on the upper right corner. There's 4 of them horizontal and 4 of them vertical, and they're stretched out thin. But basically, they, if you look below it, represent a complete bipartite graph. The couplings are, there where they cross. And basically, that little unit cell there, when we're talking about the problems on the graphs, it's a complete bipartite graph on 8 vertices. And the horizontal ones, Q5, Q6, Q7, are connected to the cells to the left and the right. And the vertical ones, Q1, 2, Q2, 3, Q4, are connected to the qubits north and south. And from these unit cells, you build a grid that is called the chimera topology. And that's the graph, the native graph, on which you can define your problems. So this is, it's basically 8 by n for whatever chimera size you have. And so C12 is not, it's not 1,024 qubits, it's 1,000, it's not a power of 2 necessarily is what I'm trying to say. It's 1152 qubits, and then if you count up all the edges between them, you get 3,360 edges. All right? So that's the graph we have to work with. Yes?
Yeah, the picture you showed, I think it's 2 slides back, that whole cabinet, including refrigeration and everything. What would be the energy use sort of at full, so if it was running at, I'm not sure if it's, what's the energy usage when this is fully operational and running computations?
Like power draw as a computer?
Yeah.
It's like a commercial refrigerator. It's not more than it's not much at all,
So your
basically.
power draw essentially is the refrigeration.
Is the refrigeration unit, yeah. It's because, basically the whole point is you can't really put a lot of energy in there, and you can't generate a lot of energy to drive these things. And when they're so cold, they're superconducting, they don't need energy. So the chip itself, you've got like a couple Xenon processors, and you've got a refrigerator, and it's the refrigeration unit, basically. So, that makes it attractive to people who might want to replace a room full of CPUs. The yearly energy costs will go way down. Yeah, so this is basically the chimera graph, but there's a lot of difference between the ideal and actual practice. They design these chips, they send them off for fabrication, they come back, and as a general rule, some of the qubits can't be calibrated to get within spec, and they have to not be used. So what you really have to work with is a subgraph of the chimera graph with certain qubits missing. And in any particular D-wave device, there's a graph like this, which is actually the working graph on which we define our problems. And basically this means that your H's and your J's, you can only have an H where there is an actual physical qubit, and you can only have a J where there's actually physically an edge between the qubits, a non-zero J, I mean to say. And that limits the problem that you can define natively, directly on the hardware. Okay, which seems like an inconvenience, but yes?
Is it possible in future to have a fully connected graph instead of chimera?
I'm not the physicist. It's certainly possible to increase the connectivity. I think that, there's no computing device that, gates have limited fan in and fan out, and fully, and networks are never all-to-all connected. So I guess, I don't know. It's possible to increase the connectivity of the cells quite a bit. You're kind of limited by how far you have to stretch them to get across each other, but more can be done in that department. Full all-to-all connectivity, I don't know. I think it might be kind of hard, basically, yeah. I think that the Google group is trying to, aren't they trying to make like 10 qubits all-to-all or something like that? I guess I don't really know. So, I mean, there are attempts in gate model to make all-to-all connectivity into qubits, and they get 5 of them put together and then they don't work. It doesn't scale. And so the thing about this chimera topology is it can scale because you can just lay out these cells. It is non-planar, so your problems are still NP hard. And and so that's kind of inconvenient if you're only limited to defining problems on this graph. It turns out it's not a killer objection. Because what happens is any logical graph, you can take an arbitrary logical graph, and it's known how to map it onto the physical hardware using minor embedding. Okay? Minor embedding is like embedding, if you know what embedding is, like it just take this graph and map it to the other graph. But basically what you're allowed to do in minor embedding is you can take a single node in your logical graph, I've circled that yellow one, and you're allowed to spread it out. You can see I've replicated it 1, 2, 3, 4, 5 times. I didn't do this, but the guy who drew the pictures did. And you can take that single logical node and you can spread it out and map it to these these physical qubits, and you can find a way to take any logical graph, and map it onto the chimera graph. The theory tells us that the worst case is a complete graph, and you only need n squared over 2-ish chimera nodes to map it onto. That's a little bit doesn't apply because of the dark qubits. That assumes a perfect chimera graph. But so there's some sort of expansion of the problem size that occurs when you do this mapping. There are, it's actually open problem whether, what is the complexity of take a minor embedding onto a chimera graph. It's NP hard to minor embed onto general graphs, but this is kind of restriction, and it could be polynomial time. But basically we use a heuristic to map general problems onto these chimera structures. All right? So you got your problem. You use standard techniques of computer science to map your problem to Ising model. Transform the problem into Ising model. Now you've got Ising model defined on a general graph, and you use this minor embedding to map it onto the physical graph. You're good to go. And so basically, that's what I just said. You can take your problem, you can send it over the internet if you like, if you have an account. or across the, if you got one in the basement, you just have to send it across the network. And there's a front-end server. The front-end server, receives problems and sets up the problem, sends it to the quantum processing unit. The quantum processing unit programs it. That's sort of that orange band that's kind of thick. It takes some time to that's actually the dominant time right now. And then it runs some number of anneals, anneal read, anneal read, anneal read, anneal read, and then it returns back a batch of solutions to you. There's possibly some post-processing that you can choose at your option. So if you're really going to run the thing, that's how it works, basically. And so what does the QPU, the quantum processing unit, do? It's carrying out this Hamiltonian. It's starting with a physical, these are Hamiltonians written in physics language now. The sigma xi is more or less analogous to your spin, except it's that three-dimensional in quantum space, in complex space ball. And you've got another Hamiltonian that's your final Hamiltonian. You specify these functions, you go up and you go down. And that's an anneal. Did I just go lost? That's all right. You can hear me, right? Okay, it's all good. And it's all physics, it all works, right? I'll try this. Is that better? No. All right, I'm lost. There it is. Thank you. All right. Alrighty, so how long does it take? Well, these are typical runtimes. The programming on the D-Wave 2X, which is a 12 by 12 chimerograph, that's the one. That's why we say 1,000 qubits. It's actually, the complete chimerograph is 1,152, but some are missing. Spec is it has to be at least 1,000 qubits, and that's kind of what you go with. It takes 50 milliseconds to program it, more or less. Different machines have different times because they're always trying different things. The anneal time is at least 20 microseconds. That's the quantum algorithm can actually run much faster, we think. But the control system, the control signals, the classical part of it that's sending the signals to the qubits needs at least 20 microseconds. So that you can actually set that to whatever you like as long as it's no less than 20 microseconds. And then readout is 210 microseconds. So the total time is programming time plus however many reads plus, anneal time plus readout time. And you can see that it's spending all of its time in I/O, and the actual anneals are the smallest part of the computation. But that's why we hire quantum engineers to make that stuff go away. So that's the kind of thing that they're trying to improve. When I say these are early days, that's the kind of thing that they're always trying to get better and so forth. So one kind of interesting thing about this is, you ask what's the asymptotic runtime? Well, it doesn't depend on n, the problem size, so it's really hard to. It's not working. Oh, okay. Sure. Pay no attention to that guy. The AQC theory tells us that your probability of a successful outcome depends on TA, right? Slower, more likely, faster, less likely. And so, but you don't know how to compute what G is, so, and it could be far less than the 20 microseconds for all we know. So, that's where the problem of analyzing performance comes in. There's all this stuff we don't actually have a model for. We just have to try stuff. Yes?
Have you found any problems where 20 microseconds wasn't enough?
As a general rule, we have found that 20 microseconds is the best setting to set it at. So as a general rule, there are, I would say, some contrived problems, where you just kind of set up this artificial thing, and you can make it do better by taking 20 microseconds. So yes, there are, but they're kind of unusual and contrived in order to sort of test that. So whether real problems, need that. Okay, right, I'll give this to you. Should we all just take a break and wait for them? It's all yours. Oops, maybe I did turn it off. No, it's the batteries. All right. That's okay. I've been a professor all my life. Yes.
So I'm curious when you say no direct time dependence on n. So first of all, how do we know that the spectral gap isn't dependent on n after all? Maybe that's what you mean by direct.
Direct, that's exactly what I mean. There's
Okay.
indirect dependence on n because generally as problems get bigger, one expects the spectral gap to get smaller, and therefore you need longer anneal times. But that's indirect, and we don't understand what the relationship is between those two things.
Totally fair. And second question, how do we know that the programming time, as we have to go from C12 to C24 to C36, for example, that wouldn't increase? Do the physicists know that?
No, they don't know that. It turns out to be the case that every time they've come up with a new model that's twice as big, the programming time has gotten smaller. But that's due to like good programming skills. I don't think that they can get, it will continue to get smaller as far as, they're sitting around arguing about the next few generations, and so they know how to make it smaller. The readout time actually is like readout time per qubit. It's a little harder to keep that, the number of qubits doubles, and they have not doubled the readout times, but sometimes they increase a little bit per problem size. Thank you. So, that's what I mean by not directly. There's not like in classical, you can count how many loop iterations and you can kind of figure things out. It's indirect. So we're trying to build these models. Is this too loud now? These performance models that describe the performance of this device with respect to the input properties and especially the input size. And we don't have any for loops counts or anything like that to go on. You just got to shut the box and see what happens and try to infer what was going on inside from the outputs that you receive. All right, so building a performance model. I just basically want to talk about some surprises, ways in which the actual device didn't end up matching what the theory told us was supposed to happen, and then I'll get to actual results and give you an idea of what we know so far about how fast it is and how fast it might be. So first off, there's this, especially if you go to the press and if you go to the scientific articles, there's like every time any experimental result is published, it basically is treated like quantum computing can beat classical computing. I saw a headline actually, Canadian computers can beat all you American computers. There's this sort of, go Canada. So there's this sense in which, any experimental result is seen as a signature for the entire complexity class or the entire model, and it just ain't true. And there's, a lot of people, pull me aside and saying, but look, is it quantum polynomial time? And I'm telling you, I don't know. And I just want to point out that it's kind of ridiculous to ask. I mean, here it's like you're asking the empiricists to solve P equals NP with an experiment, comparing one algorithm to another algorithm. It's just not going to happen. It's a question for the theoreticians to sort out. I don't have any idea what the implications are for all of these complexity questions. And I personally, based upon my authority of years of experience doing this, don't believe that such an experiment can be designed. So there. So just don't get all excited about what this all means. And that's basically what I said. The questions that they're asking in complexity theory about NP and NP completeness and what's it called, quantum Arthur Merlin and quantum Merlin Arthur and all those things, those statements are formulated with upside down A's, universal quantifiers. And no experiment ever designed can deal with universality in infinite classes. You can only come up with, there exists a phenomenon, I've demonstrated it, and they just can't be used to approach this larger problem. So I'm not going to try it, and we just have to suck it up and be careful, be reserved in what we hope for. All right, so there's my little defensive, I don't know. answer. Okay, so, but in the meantime, we can try to understand how this works. We can try to understand what makes problems easy and what makes problems hard, and how to predict performance. We can start building our knowledge base to make those kinds of predictions, and that's really what I do at D-Wave, is try to build understanding of how it works. So let me just point out that building performance models when you're evaluating heuristics for NP-hard problems is not easy by any means. And one problem is these heuristics don't ever, you ask how much time does it take to solve the problem? Well, they're not meant to solve problems. These are optimization problems. You can spend more time and get better solutions, or less time and get worse solutions, but nobody knows what the optimal solution is, so you never know if you've reached it. And you just, if you knew that it was the optimal solution, then why are you, asking the heuristic to, there's this whole sort of premise that you just run these things and try to understand that convergence curve, the relationship between effort spent and quality of solution that you return. And you can get different algorithms that have different performance profiles and behave, some are better, some are worse, depending upon how you decide to measure that. Very commonly, since this is a curve, we'll take a vertical slice and say who got the best solution when I gave them all the same amount of time, the same amount of effort. Or we can say, let's make a target solution cost, and we'll race them all and see how fast they got to the, which one got there faster. So those are kind of two basic approaches. There are fancier approaches with Pareto optimal curves, like which curve dominates in which space, but they're a little more sophisticated. So when you say which one's faster, the first reply is, what do you mean by faster? Yeah, so.
Couldn't you just use the optimization as a decision? Right, and then like, how fast can you get a good enough solution that satisfies the decision problem?
If I...
Give a very concrete comparison, right?
Yeah, if I understand you correctly, finding the optimal solution is usually mapped to solving the decision problem, yes or no. But we measure these things, we don't actually know what the optimal is, right?
So start with the decision problem. Right.
Right. So here's what happens. The decision for traveling salesman, the decision problem is there a tour of cost less than X, right? And now I run this optimizer, and it gives me a tour of cost less than X, and I say yes. But if it doesn't give me an answer less than X, I don't know if there is an optimal solution less than X. So it's like a one-sided decision problem solver that doesn't work if you don't know, if it says no, you don't know if the answer is yes or no. So you can kind of use it in a halfway, but when the problems are hard, and it never says, finding the bottom it's always going to say no, and it's sort of, or with high probability they're going to say no because they're NP hard to solve. Yeah. All right?
For benchmarking, right, you can even construct artificial examples, right, and know the answer. So for the purpose of comparison, right?
Yeah, you can absolutely construct problems that by construction you know what the optimal solution is. It's hard to argue that they're especially hard or challenging, and so what happens is all the solvers find the same answers, and that's a viable approach, and it works well in many cases, but it's not the perfect approach. It doesn't always tell you what you want to know. And you can always at least they're minimization problems. So even if you don't know what the optimal is, you can tell which is better and which is worse because smaller is better, right? So at least you have a direction in which to go. All right, so that's kind of what we want to do, is take this new D-Wave machine and evaluate it with the understanding that there's a lot of different ways you could evaluate it. And here we go, empirical surprise number 1. So here is a chart showing the D-Wave machine in red, and basically the blue curve is good old simulated annealing. And we do have this idea that if you increase the annealing time, you're spending more time per anneal, you tend to get better solutions. And you can see that curve doing just what it's supposed to do from the previous from the previous slide. The bottom, diamonds on the bottom are optimal solutions. The red curve is the D-wave curve, and actually, changing the anneal time empirically doesn't really seem to affect things most of the time. We can come up with these contrived cases, but as a general rule, it just kind of sits there, right? So much for everything I just told you about how to evaluate heuristics. And basically, so the question is, why might that be? And basically, the conjecture is, the belief is, this is more than a conjecture, that the quantum algorithm is actually converging way faster than, this is what I've been saying, the classical system allows it to converge. So this is our 20 microseconds right here, but it does converge down, maybe down in the nanoseconds or whatever. We have no idea. I mean, the physicists have some idea, but, and we just can't see it converging because it's sitting out. Yes?
I'm just wondering, the annealing time here refers to how long the machine is doing the anneal process. What does that mean in terms of simulated annealing, which is a discrete?
Yeah, so you can implement it on a Xeon Intel machine and measure how many times per anneal. This is a particular implementation of simulated annealing that is used on these. It works well in these chimeragraphs where, if you're familiar with simulated annealing, it has these anneal steps and the temperature goes down. Inside that loop is another loop that goes through every vertex. So that's called a sweep. You've got a certain temperature, you sweep through all of your vertices, flipping them or not flipping them, and then you change the temperature, and then you sweep through all the vertices, and then you sweep through all the vertices. So the time per anneal is basically how many sweeps you specify. A few sweeps and it's a short anneal, and many sweeps and it's a long anneal. And these are physical runtime measurements on a recent Intel device. So there is that, you specify iterations, and the iterations are being reflected in runtimes here. All right? So, basically getting up the time. On the one hand, simulated annealing is about, on this particular input, it's about 10, maybe 50 times slower, but give it 50 times the amount of time, and it can reach a common, the same kind of solution quality, and then you give it more time and it gets even better. But it takes longer to get to that place is basically what we're seeing here. All right? Do I have 1 minute? What's my time? Anybody?
There's one up there.
Oh, yeah.
But that's not right. Oh, maybe it is. What time did we start?
Yeah, it is.
3:30?
Yeah.
So I'm 10 minutes past? Because my little thing says just an hour.
We started about 7 minutes late.
Yeah.
Oh, okay. All right. I'll take my 7 minutes then. All right. All right. So fine. What we typically do is just set the anneal time to 20 microseconds because that seems to be the best thing to do. And we check it. But and then you take these 1,000 samples, and you can see that you can get a lot of samples. There's this delay from of about, in this case, it was probably 30 milliseconds. And then you can get bang, 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 bang. You can get these samples coming out. This is anneal read, anneal read, anneal read. And the average energy is that horizontal gray line. And you compare this to 2 other classical heuristics. And you can see that these convergence, you can see just looking at the minimum solution in the sample, that's what these convergence curves on the left look like. So you can think about how, given that you've got fixed anneal time and you set your parameters, this is simulated annealing with 500 sweeps and simulated annealing with 1,000 sweeps. You can see that they converge, and in different ways. So the interesting thing is, what about this different convergence patterns? And basically, what seems to be happening is the D-wave quantum annealer. This is that hull of the minimum cost. It just drops like a rock to this little area that's like epsilon above optimal. They've got models, and you can use problems where you know the ground state. And there's epsilon has got a definition that I won't go into. And then it spends all of its time in this other region not getting any better, right? It's just not converging. And this is like factors of 1,000 difference. I mean, it's spending, it immediately drops, and then it can spend 99.9% of its runtime in this other area, never quite getting down, dropping that last little bit. Yes?
So is that to basically fit the noise floor of your machine?
It's totally the noise, yeah. So again, why would that be? And it's the noise, the analog noise, the control signal noise, the thermal temperature, that little 20 millikelvin, is affecting the computation, but basically it's kind of focusing, the effect is focused on that little gap between optimal and non-optimal. And it's quantum algorithm is doing a very nice job of getting to close to optimal. But here's a case where we have problems of size around 500. And you can see these are, I won't go into details, but you can see that the time to get to the optimal solution is growing, and there's a lot of noise, there's huge variance and everything. But if you, instead of finding the optimal solution, if you're willing to settle for third best or better, first, second, or third best solution in the space of 2 to the 512, you can find that 1,000 times faster. So, so that's cool. You know, that, I mean, this is you know, a useful thing to have learned. It's really just something we've kind of figured out. And as suggested, this is due to intrinsic control errors, which are actually not. It's this is a typo. It's integrated control errors, not intrinsic. Because of these imperfect analog signals, and there's little physical biases in the qubits and things, the Hamiltonian that the user sends to the problem gets perturbed a little bit, and by the time it reaches the chip, it's slightly different. And those small perturbations can, on occasion, make it solve a different problem with a different ground state than the one that the user specified. And those little errors are showing up as an inability to seal the deal and get across that little line there. So, all right, that's progress. We understand these things, and that's great. And so, you know, the next question is, okay, how do we mitigate that? How do we fix that? And that's kind of what the engineers, you know, get up every day and fight about better ways to get this little band under control. As a user, there are a lot of things you can do. You can change your Hamiltonian in certain ways. You can rescale the problem in certain ways. You can use a different embedding we're learning recently. And there are techniques of quantum, you know, there are different things you can do. You can post-process the samples and things. So we've developed these tuning methods, we call them, to sort of get better to, since it's the classical problem, we use classical remedies to get out of that place. And my problem as a person trying to evaluate is how do I separate the error, the signal from the noise? You know, what's the quantum algorithm doing from the behavior that's really imposed by the control system? And you know, it's certainly reasonable to test the machine we have in hand, and we want to understand how it behaves as is. But the point is that the engineers are making the noise thing better. It's never going to go away completely, but if whatever I measure today just isn't true next year when the next model comes out, then I'm not learning a lot about how the whole thing works. So we're always trying to separate these two things and get a better understanding. So I think I'll just make one more slide, then I know I'm imposing on you at this point. So there was this recent paper, if you follow the literature, what is the power of coherent tunneling, and this paper by the Google group, and they showed 100 million times speed up over, I have to say that in a booming voice, over simulated annealing and the quantum Monte Carlo algorithm on a particular input. And we all kind of know that one input does not make a summer, but still it kind of illustrates that there's something going on, that you know, there is a power that can be harnessed. And, but the other kind of more interesting point was that they predicted, based upon their earlier D-Wave 2, then they got the D-Wave 2X, which was 500 qubits to 1,000 qubits. And based upon the D-Wave 2, they made these predictions. They ran this experiment. It took months and months of computation time to get the the slow, I mean, this is, you think about 10 to the 13 microseconds, that's 10 to the 9 seconds, right? Did I do that right? 10 to the 10 seconds, pi seconds in a nanocentury, so 3.3 seconds is 30 years. This is a significant computation. They used up like all of the Google Cloud apparently, and it took them, you know, a long, long time to get those data points, those red and green data points up there. But it was really fast. But one thing that was interesting is based upon their previous model, they actually predicted that the blue curve, the D-wave machine, would be 1,000 times slower than it was. And this was this point about making better technology. It does, you can't trust any curve that you're seeing this year because it's going to be a different curve next year. And so that's what makes it interesting. So how fast is it? I'm going to, whoops, just fast forward. That's how fast it is, and that. And there we go again, and that's how fast it is. We're working on understanding this whole thing even better and looking at new problems, like instead of just finding an optimal solution, a lot of applications, you know, obviously we can get great samples, we can get a lot of samples, and looking at the diversity in those samples and seeing if we can get a lot of unique solutions, and rather than just the same solution over and over is an interesting new area. So, all right, cut to the chase. Yes?
So simulated annealing in sort of the general optimization community is famously slow. And so are there comparisons against, I mean, like Groundholder and get one of his really good heuristics for something, against fast heuristic solvers? Yeah,
so yes and no. We do have a pool of fast heuristic solvers. The ones I've compared against CPlex, and it beats CPlex. And but so part of the problem is you take your original satisfiability problem and then you transform it to Ising model, and then you map it to the chip. And you have to, in order to fit it on the chips that have been built so far, 1,000 qubits sounds like a lot, but these are 30 variable problems or something. And so yeah, there have been comparisons done to satisfiability, and there's a job shop scheduling paper. There's a paper on database query optimization. So people are learning how to take these problems, but they're still small. And if you're solving a 30 variable problem, it's fast, and you can't, you know, if you've got a 20 microsecond lower bound, you can't, we're not at a place yet where we can really tell, basically. But that's, you know, a bright future ahead of us, certainly. Yes?
Okay, your comparisons with simulated annealing, you kept comparing on time. Now, in current conventional computing, hardware is free, and we pay for computing by the kilowatt hour. Now, your hardware is in its infancy, so I'm not going to worry about its price tag. But it takes a lot of kilowatt hours to get something down to...
Yeah, and certainly, you know, we did the back of the envelope calculation with the Google result. Yeah, you know, because it's 100 million times faster and they used the cloud, they were really using a lot of kilowatt hours. I don't know that anyone has done it for just, you know, more conventional problems that don't show that big of a speed up. But that's a kind of a thing to keep in mind, because this thing draws power like a refrigerator, and it doesn't draw power like a rack full of computers. And so that's definitely kind of a thing to keep in mind. Oh, you were talking about simulated annealing being famously slow. The version implemented here that is tuned to the chimerograph and has all these tricks is actually one of the two fastest ones. There's another one called HFS that works by optimizing low tree width subgraphs and then patching them up. And so when we're looking at problems directly on the native problem, it's simulated annealing in general can, you know, be mixed, but these are quite fast implementations. Anything else? Yes?
So I'm curious about this argument regarding decomposition, because it will, I mean, that's where the power of conventional computing comes from, right? You have a CPU that can actually do limited things within one operation, and then you just know that you can use a chain of operations, some of them executed in parallel, to solve your problem. that's a little less clear here, right? How to actually do the decomposition, so that you can solve the pieces, map the pieces on your chimera graph, anneal them separately, and then piece them together.
Yeah, and certainly you can't verify, you can't guarantee optimality if you're going to approach the problem that way. And yeah, there's a whole wide world of how might I just actually saw. There's a whole conference on decomposition algorithms for heuristics, I think next year. But so I guess the point is, if you can establish that it's doing well on the problems it can solve, then if those problems are part of a larger, yeah, there's a huge question there. And there have been some. I know at 1QBit there was a paper recently on fellow behind you is from 1QBit on decomposing. Problems, in that way, but basically it's like a potential application that has only been explored in limited ways.
So you would then say that this is still a considerable challenge. It's far from solving.
To know how to do it, yeah. And there are research groups actively working on it, but yeah, there's the overhead of you want to figure out how to map it in such a way that you don't have to map in your inner loop. You want to be able to do that once, and then and so there are ideas that seem promising, but again, who knows? It's wide open.
I mean, for two-weighted map set, for example, one of the kind of basic problems you mentioned earlier, I think that's actually really not clear at all how you would do that.
How you would decompose? Well, how you would decompose random problems? Absolutely. A lot of problems that arise in practice are maybe a little regular, and they have certain cut sizes, and you can maybe apply domain-specific knowledge in some ways. There's a paper that solves a constraint programming problem based on satisfiability. It's a circuit fault analysis, where you've got the circuits and you give it and they've got it in a loop where they're querying the hardware to find what the inputs, to identify it. And it does use some decomposition, and it is faster than anything they know classically, but it's, again, very early days.
Yeah.
Hard to tell. Yeah. Anything else? All your questions about quantum computing have been answered? That's fabulous. Yes?
Just on the isolation, it sounds like there's another, it's an engineering field outside of this that experimenting with fewer numbers of millikelvins and how that.
Yeah, like there's a whole team that's not computer scientists, they're quantum engineers. Colder is better. How can you get a refrigerator to stay really cold for like 18 months because if it warms up the chip, it doesn't ruin the chip, but it won't, you get too much thermal noise and it's just random outputs. So there's a lot of technology involved.
On the noise isolation part, if it's cosmic radiation, sure, there are one-offs and you're just stuck. You blind
Wait,
as
yeah.
much lead as you can buy, I guess. But on things, the example you gave of the earthquakes in California affecting your results, that's macroscopic, so you'd think you'd be able to do something like noise-canceling headphones where you'd have external detectors for these macroscopic.
Put them up on springs somehow, yeah.
Well, no, just know what they are and compensate for them in the inner calculation.
Yeah, I don't know a lot about how what they do and how that all works. There might very well be those kind of things. I don't really. I know a lot of, the fact is you have wires coming from room temperature and going down to the chip, and there's like a hole in your perfect protection because you have to use the wires to control the chip. So, I think their shielding from the outside is pretty good. I don't know if it's electrical itself, because also anything that's using energy to shield you is going to, itself could cause problems. So, but I don't know. I don't really know much about it. Yes?
So instead of solving decision or optimization problems, could you solve counting problems, like counting the probability?
Oh yeah, sure. Well, you can sample. You can. I would say that's as we speak. There are people trying to figure that out. You can sample. If you can get a diverse enough sample, you could heuristically count. This thing is never going to guarantee to find all all optimal solutions for you, right? It's a heuristic. But there are heuristic ideas for estimating the size, the number of optimal solutions.
There's no way to get at the superposition information?
No, because that would be, that's Schrodinger's cat. You have to shut the door and run it and then open the door. And if you look at it while it runs, it'll screw up. Basically observing a quantum process means, when I observe you, I'm bouncing electrons off of you and they're coming into my eye, right? And we can't have electrons bouncing off the, any kind of observation. Basically, it means reflecting something off the thing you're trying to observe, and that's why quantum processes just can't tolerate that kind of snooping on their behavior, because it'll destroy the superposition, the entanglement with me observing it will destroy it. That's kind of the catch-22. There are things, they have, physicists can do things. They send these probe qubits, and the state of that one tells you what the state of this one was back when we ran it. There are sophisticated physics experiments you can do, but basically, you got to run the thing in isolation. Yeah. Yes?
The size of the chimera graph is kind of one dimension of how hard the problem could be. The other would be the fidelity of the H and J's, like how big and small the differences can these numbers be? Can I encode more information in that?
Yeah.
For the D-wave machines, what kind of range of H and J?
Yeah, so to run these things, it's hard to say. It's hard to give you a quick summary, but basically it takes floats as inputs. You can specify your H's and J's as floats. But the fact is, the precision, what happens is all those floats get scaled down to an electrical range that's like +1, -1. And if you've got a lot of precision in there, it's not going to work. And so, precision matters when, the problem with precision is if you've got two H's and they're fighting each other, if they both agree, then it doesn't matter how precise they are. The spins will both go up. It's when they disagree and you're adding them up and the precision is wrong, and it's going to choose based upon an error like that. So it's based upon how much, it's called frustration, how much disagreement there is in the graph. If there's a lot of frustration, then precision is a problem. If there's not a lot of frustration, then precision isn't a problem. So maybe integer weights. The fact is integer weights between +10 and -10 are. I don't know.
Maybe that's the kind of range where we're
Yeah. A lot of problems we work at, we keep our integers in a range like that, and then it gets scaled down to, appropriately. But it's really hard to generalize because sometimes it matters and sometimes it doesn't.
That scaling process is an analog scaling.
Yeah.
So there's no digitization error.
Right. Yeah. Yes.
Will D-Wave compete against supercomputers?
Well, if you can go 100 million times faster than, that was just a single CPU, but it took months it was a big thing on the web. Yes, it could possibly. Will it? I don't know any more than anybody else. That's kind of the goal, is to figure out how to harness this so that you can replace supercomputer computations. Whether that'll pan out, it really is very early days, and there's a whole lot we don't know. So, all right.
Okay, we should probably wrap up. Thank you.